Welcome to your video covering learning target number 6B. In this video, we are going to cover how we are able to use data collected by a calorimeter investigation to calculate the enthalpy of reaction or the enthalpy of a physical change or the specific heat of a substance. So step one, what is a calorimeter? So a calorimeter is a device that's insulated. A reaction or physical process is performed on the inside, and since it's insulated, the heat lost by the reaction is trapped inside the calorimeter, and you can measure the temperature change and thereby calculate the heat transfer or the amount of heat. There are two types of calorimeters. I'm holding up a standard calorimeter, otherwise known as a coffee cup calorimeter, because you can make your own using coffee cups at home. This is not a coffee cup, but it's styrofoam. There's these components here. You've got your insulated container, insulated lid, a hole for just the thermometer to fit through, a hole for a stirring stick to fit through. This group who made theirs last year put in a magnetic stir bar on the inside and put it on top of a magnetic plate so you could stir without touching it. And inside of the calorimeter, you put an amount of water and whatever else in there that you want to measure the heat transfer. And you perform your reaction, watch the temperature go up. Bomb calorimeter is the second type. And a bomb calorimeter is used when you're not going to change the volume of the reactants, rather you're just going to change the pressure on the inside. The coffee cup calorimeter, the volumes are changing. In the bomb calorimeter, volumes are not going to change. So if we want to figure out the calorie content in particular types of food, we use a bomb. The bomb calorimeter is still an insulated container that has water in there. But inside, this is the bomb part right here, where the fuel is the food. You have two electrodes that are connecting to the food. An electrical current is what ignites that food so it combusts. As it combusts, the heat transfers from the food into the water, the temperature rises, and then you can see where the final temperature ends up at the end of the combustion reaction. We're going to talk more about the bomb calorimeter in the third video. There's 3 to this series. We're going to take a moment and talk about how a coffee calorimeter works, and we're going to work through a calculation using a coffee cup calorimeter to find the specific heat of silver. So I'm going to read through this and then I'm going to show you the simulation. So first, when we have a coffee cup calorimeter, we fill it up with a given volume of water. Now, if I know the volume of water in milliliters, I will know the mass of the water in grams because 1 milliliter is equal to 1 gram. I'm going to also measure the initial temperature of the water. Then I'm going to take my piece of silver, my sample, I'm going to heat that up to as high of a temperature as I can get. If you were in the lab doing this, you'd be heating it up in boiling water so you can control the temperature and would get up to 100 degrees Celsius. Then you quickly open up the lid of the calorimeter, you throw the metal in, you seal it up as fast as possible, you stir and you watch the temperature increase. And when this temperature stops changing and begins to decrease, you record that peak temperature as the final temperature of both the metal and of the water. So let's look at how this works. So here is your calorimeter. I'm going to choose silver, and the goal here is to prove that the specific heat of silver is going to be 0.234 joules per grams degrees Kelvin, or degrees Celsius. I set the initial mass of the silver to 20. I'm going to raise that temperature of silver to 100, and the simulation's really finicky, so getting it to exactly 100 is going to be difficult. And I'm going to say 102 because I'm not going to mess with that too much. The initial mass of the water is going to be 30, and the initial temperature of the water is going to also be 20 degrees Celsius. Everything here is in 4 or 5 sig figs, but you'll see on the data that I collected, we're going to do 3 sig figs. So here we go. I heated up the silver to 102 degrees Celsius, and I'm going to throw it in the calorimeter. If you were doing this in the classroom, you would have a temperature probe in there to get this exact same graph, where temperature's on the y, time's on the x, and you're seeing a linear function start to form, and you're looking for a plateau and then a drop. I'm not going to let this go too long. This is going to be where your plateau is going to end up. Notice that it's kind of slowing down, and my uncertain digit is very uncertain. So I'm going to call this temperature here 22.9 degrees Celsius as my final temperature of both my metal and of my water. Let's look at these calculations now. So the secret of calorimetry is that if I know how much heat was gained by the water, I will be able to calculate exactly how much heat was lost by the reaction, and in this case, it's going to be the metal. So the goal is to prove that the specific heat of silver is once again 0.234 joules per gram kelvins, and there's my data table. So I'm going to first go through and calculate the amount of heat that was gained by the water. So I'm going to go here like this, and I am going to say blue for water. The heat gained by the water is going to be the mass of the water, the specific heat of the water, and the change in temperature of the water. Cum-cat, cum-sat, cum-cat. And I know my mass of my water was 30. I'm going to call it 30.0 to do 3 sig figs. My specific heat is 4.18. And my final temperature was 22.9. My initial temperature is 20.0. So I'm going to throw all of that into my calculator. I'm going to say 30 times 4.18 times 22.9 minus 20. And I'm going to find that I gained 364 joules worth of heat. 364 joules worth of heat was gained with 3 sig figs. So if I know the amount of heat gained by the water, it's going to be equal and opposite to the heat lost by the silver. So the silver gave the water 364 joules. So now what I'm going to do is I'm going to use cum-sat again, or cum-cat, and I'm going to rearrange this equation to isolate specific heat, because I'm trying to prove that the specific heat of silver is 0.134 joules per gram kelvins. So I'm going to divide both sides by mass and change in temperature. Mass, change in temperature. Boom, boom. And I'm ready to fill in. So negative 364 is my heat. My mass is going to be mass of the silver was 20.0. And my change in temperature, I went down to 22.9 from a starting location of 100. So I'm going to take a moment and put this all into the calculator and hope we're really close to the specific heat of silver. Negative 364 divided by 20 times 22.9 minus 100. And I did not get too close to silver, but that's because I didn't let the simulation run long enough. And I find that my specific heat is going to be 0.236 joules for every gram degree Celsius. So if I click back and double check that with my simulation, they got 234, we got 236, so we're close enough. All right, so this is part one. Part two is going to be doing this exact same type of process, but instead with a chemical reaction that's exothermic. And then the third video is going to be about bomb calorimetry, which should interest the people that are doing bomb calorimetry work for your IAs. So thank you for joining us, and we'll see you soon.